Hi class, Mrs. Thomas here. Today let's talk about factoring. In this video we're going to talk about common factoring, simple trinomials, difference of squares, grouping, factoring by decomposition, and perfect trinomial squares. So first let's look at common factoring. So common factoring is something you always want to check for first. And what that means is we look at all of the terms in our polynomial. So let's look at A first. So let's say we have a polynomial. In this case, it is a binomial because there's only two terms that we're looking at. And we try to decide what do those two terms have in common, right? So if I'm looking at 24x squared, and I've got 30x as my second term, I want to try and break down those numbers into all of their different multiples and find out what their biggest common factor is. So in this case, our biggest common factor is a 6. As I know that 6 goes into 24 4 times and 6 goes into 35 times. And I also look at the variables, and here my variable that is in common with both of them is x. So I can pull out a 6x, and then in my brackets I try to think about what times 6x is going to equal 24x squared. So it's kind of like I'm dividing 24x squared by 6x. So I can multiply 6 times 4 to get 24, and I can multiply x times another x to get x squared. So 6x times 4x equals 24x squared. Similarly, I think 6x times what is going to equal 30x, and I have minus 5. So 6 times minus 5 equals negative 30, and x times, in this case, there's no x over here, so that x would just carry on over. So let's look at something a little more complicated. So here we have a trinomial, and it looks like there's at least a p in every single term, and I've got negative 42, negative 28, and negative 3. So I have three numbers that all have a common factor of negative 7. Now it's really tempting to do positive 7 here, but since all three of those numbers are negative, I do recommend that you pull out the negative as well. That way we can keep all of the numbers inside of our brackets positive. And then I have to look at my variable, and I'm looking for the variable that has the smallest exponent. So the smallest exponent in this case is p squared. So I'm going to pull out that p squared. And then I have to think about what number times negative 7 equals 42. So my first one is 6. And then I have to think how many p's are left over, right? So p times p squared would equal p cubed. So when I'm pulling out negative 7p squared from negative 42p cubed, I have 6p. I'm going to do the same thing with my other terms. So I have negative 7 times positive 4 in this case, and then p squared times p squared would equal p to the 4, and then negative 7 times positive 5 would equal negative 35, and then p squared times nothing would equal p squared over there. So these are examples of common factoring. Next, let's look at simple trinomials. So these simple trinomials are, we're going to look at first just quadratics. So these are of the form x squared plus bx plus c. Normally quadratics will be of the form ax squared plus bx plus c. But for simple trinomials, a is equal to 1, right? So when a is equal to 1, Well, it actually kind of simplifies our factoring process. So we're going to use a method called product sum method. So let's look at the example x squared minus 3x minus 10. And what I need to do is come up with two numbers that multiply to 1 times negative 10. So they multiply to negative 10, and they add to negative 3. So I can break down 10 into all of its different factors. So I could break down 10. So I think two numbers that multiply to negative 10. Well, I could do 10 and negative 1. I could do negative 10 and positive 1. But 10 and negative 1 would add to 9, and negative 10 and 1 would add to negative 9. So we know that neither of those are my case. Other products, I also have a negative 2 and a positive 5. So negative 2 times 5 is negative 10, but negative 2 plus 5 is equal to positive 3, so it can't be that one. I also have a positive 2 and a negative 5, and that multiplies to negative 10, but when I do 2 minus 5, that has a sum of negative 3. So that's how I know that these are my two numbers I can use when factoring my simple trinomial. And since simple trinomials are a special case, what I can do is I can jump straight to its factored state, and I can write out x plus 2 times x minus 5, and that is a factored simple trinomial. So I got my 2 and my negative 5 from the two factors that multiply to negative 10 and add to negative 3. So let's look at some more examples of that. So here we have another example, x squared minus 12x plus 20. So here I have a product of 20 and a sum of negative 12. So I could break down 20 into all of its different factors, but when I do that, I'll find that the only two numbers that multiply to positive 20 and add to negative 12 are negative 2 and negative 10. So once I have those two numbers, I can go ahead and factor my simple trinomial. So I've got x minus 2 times x minus 10. Now this also works for trinomials that have more than one variable in them, right? So let's have a look at another example. Here I have a squared plus 7ab minus 18b squared. So what I need to do in this case is I need to keep in mind that I'm going to have an a term plus a b term over here, because I know that if I were to expand it out, I'm going to have an a times an a to get a squared, and I'm going to have a b times a b to get b squared. So we can still factor this using our product sum method. So I'm still going to be looking at this c term for my product. So I have negative 18, and my sum is going to have to be this b term, which is 7. Right? And I can break this down into all of the factors to multiply to negative 18 and add to positive 7, right? In this case, I'll find that my two factors are 9 and negative 2. 9 minus 2 equals positive 7. 9 times negative 2 equals negative 18. But when I factor it out, I'm going to be left with a plus 9b times a minus 2b. And the reason why I need to add this b in there is, let's just check. We're going to check this one by expanding out again, right? So if I check to see if this factored form is actually equal to my trinomial, I can use my FOIL method. If you remember, FOIL stands for first, outside, inside, and last. So when I'm expanding out a plus 9b times a minus 2b, I'm going to multiply the first terms over here. So I have a times a, which is a squared. Then I'm going to multiply the outside terms. So this is my first, right? A times a, so the first term in this one times the first term in this one. And then I'm going to factor my outside terms, expand my outside terms. So I have a times negative 2b, so I get minus 2ab. This is my outside. And then I'm going to multiply my inside terms over here. So I have 9b times a, so I have 9ab. And then I'm going to multiply my last terms over here. So 9b times negative 2b is minus 18b squared. And then when I combine my like terms, I get a squared plus 7ab minus 18b squared. So we can see from my check that my expanded form is the same as my original trinomial form. So I do know that this is, in fact, the factored form of this trinomial. Okay, so far we've looked at common factoring, check. We've looked at simple trinomials, check. Let's talk about difference of squares. All right, so a difference of squares first, let's think about what a difference means. A difference is subtraction, right? So whenever we see this difference over here, that means that we're going to be subtracting, and squares means that we're going to be subtracting two squares numbers, right? So the form is we have one number squared minus another number squared, not necessarily x squared and y squared. So let's look at our first example here. So let's say I have x squared minus 64. So x is my variable, squared, and 64 is the square of 8. 8 times 8 is 64. When I'm factoring out a difference of squares, I'm going to get a number plus another number times a number minus another number. Difference of squares, if you remember from expanding, is caused by our center terms actually canceling out, right? So I'm going to show you what that means when we check our answer afterwards, right? So our first term is x squared. So if I want to know what this term is, our first terms are, I'm going to take the square root of x squared, which is equal to x, and I can plug that in to my format, and then I'm going to take the square root of 64, which is 8, and I'm going to plug that in to my format. So I'm left with x plus 8 times x minus 8, and this is my factored form. So once again, let's check our answer just to prove to ourselves that this form does in fact work. If I have x plus 8 times x minus 8, and I'm expanding this out using the FOIL method, I'm left with x squared plus, or in this case, minus 8x plus 8x, my inside terms, and then my last terms are minus 64. So when I'm collecting my like terms, what happens is I have this x squared here, my negative 8x and my positive 8x cancel out because of the plus and the minus in the factored form. So I'm left with just x squared, the first two terms multiplied together, minus the last two terms multiplied together, right? And this is what creates the difference of squares. So I have x times x, and I'm subtracting 8 times 8 over here. So whenever you see a difference of squares, we know that when we factor it, it's going to go back to this original form of being the square root of one number plus the square root of the second number times the square root of the first number minus the square root of the second number. So let's practice that a bit more. Let's look at some more examples. So let's look at 36y to the 4 minus 49z squared. Now, we know that this is a difference of squares. First, because we know 36 is a square. It's 6 squared, right? 6 times 6 is 36. We know that 49 is a square. 7 times 7 is 49. And then we also have even exponents. Whenever we have even exponents, we know that they are actually squares. So even exponents indicate a squared number. So if we were to take the square root of 36y to the 4, so if I had 36y to the 4, I take the square root of that, what I'm left with is 6y squared. Because 6 times 6 is 36, and y squared times y squared is y to the 4. Similarly, if I take the square root of 49z squared, I'm left with 7z. So when I need to factor this, I'm going to have 6y squared plus 7z times 6y squared minus 7z. And that's done. Now, some students also tend to ask, does it matter which one I put first? And the answer to that is no. This is also equal to 6y squared minus 7z times 6y squared plus 7z. And the reason for this is that any number times that number. So like let's say this equaled 5 and this equaled 6, right? 5 times 6 is the same as 6 times 5. So it doesn't really matter which brackets you put first. No marks would be docked for that. Okay, let's look at one more example of difference of squares. So let's say I have negative 50 plus 8b squared. Now, at first glance, this example does not really look too much like a difference of squares, right? 50 is not a square, 8 is not a squared, b squared is a squared, but at first glance, this does not look like a difference of squares. However, my binomial has something in common. I can common factor it first, right? So remember that we always need to check for common factoring. So if I common factor a negative 2, for example, out of these two terms, the first term divided by negative 2 is 25. The second term divided by negative 2 is minus 4b squared. And suddenly, a difference of squares has emerged, right? So square root of 25 is 5. Square root of 4b squared is 2b. So the factored form is 5 plus 2b times 5 minus 2b. And my negative 2 that I factored out in the first step just hangs out in front. Okay, so we've looked at difference of squares. Now let's look at grouping. So grouping is something that we can do when we are facing factoring something that is not necessarily a trinomial. So we always want to check to see if we can group if we're dealing with polynomials of 4 terms or greater. Right? So let's look at the example am plus an plus bm plus bn. So this is a polynomial where all 4 terms don't really have anything in common with all of them, right? Am has something in common with an, and it also has something in common with bm, but it doesn't have anything in common with bn. So when I check to see if I can common factor, right, I can't really common factor anything from all 4 of the terms. However, I could group together am with an and factor out an a. And if I were to do that, I would be left with an m plus n. A times m would be am, a times n would be an. And similarly, I can group together bm with bn, and I could factor out a b, and I would be left with m plus n. Now, suddenly, I notice that I now have 2 terms. So I factored my 4 terms into 2 terms. One term is a times n plus n, and my second term is b times m plus n. So what I can do is I can actually factor out the m plus n as well. So let's say I factor that out. I'm left with m plus n. I factored out the m plus n. And then I think to myself, what am I left with? So m plus n times what equals a times m plus n? Well, that's a. And then I look at my second term, m plus n times what equals b? Well, b. So m plus n times b would equal b times m plus n. And then I'm done. I'm all factored out. So sometimes when we factor out a binomial like this, right, it can be a little bit confusing. So let's pretend we're in an alternate universe. Alternate universe. So suppose m plus n equaled x. Right? So let's pretend that m plus n equaled x. Right? If this was the case, well then a times m plus n would be ax, and b times m plus n would be bx. And now it becomes really obvious that these 2 terms have an x in common. Right? So that becomes really easy to factor out. And if x is equal to m plus n, well, that means I can replace my x with m plus n. And suddenly, I am left with the same result as I got when I just factored out the full m plus n. So if this idea of going from this step to this step was confusing for you, consider replacing m plus n with an x, right? And then factoring out that x instead. And this is kind of the general idea of how when we factor out a binomial, it's the same as just factoring out a variable. Let's look at another example of factoring by grouping. So let's look at this example. Let's say we have x squared minus xy plus xz minus yz. So what I'm going to do is I'm going to look at all my terms, and well, I can factor out something from both of these terms, and I can factor out something from both of these terms. So in my first group, I can factor out an x, and I'd be left x times x would be x squared, and x times y would be xy. And then when I look at my second group, looks like I can factor out a z, and I'm left once again with x minus y. Sometimes, like when we're factoring by grouping like this, and we want to get a final answer, it's a good idea to try and make sure that in your brackets you have the same term so that we can then factor out that binomial as well, same as we did in example A, and end up with a final factored form, completely factored form, like so. All right, so understanding factoring by grouping is really important because it's part of the crucial step in learning how to factor by decomposition. So this is something that you should probably get some practice in, and rewatch the video, and also leave comments and questions. I'd be glad to go over them, see if I can address them to really make sure that you guys are understanding this particular step, because this is crucial to learn how to factor by decomposition. So let's look at some examples of factoring by decomposition. All right, so factoring by decomposition, let's look at the example A. We're going to look at 2x squared minus 7x minus 15. So similarly to the simple trinomials, so in this case, this is what we call a complex trinomial. It's called a trinomial because there's 3 terms, right? So we have a quadratic form trinomial here, ax squared plus bx plus c. This is a standard form quadratic equation, and in this case, a is not equal to 1, right? But we still start off looking for a product and sum. Only this time, we're going to be multiplying our a term times our c term for our product. So we're going to be looking for a product of 2 times negative 15, and that is a negative 30 product. And we're going to look for a sum of our b term, which in this case is negative 7. So we need 2 numbers that multiply to negative 30 and add to negative 7. So we can break negative 30 down into all of its factors. Negative 30 times 1, for example, is a possible combination, but that doesn't add up to negative 7. So if we look at all of the different factors that multiply to negative 30, we can find that the combination of negative 10 and positive 3 will multiply to negative 30 and add to negative 7. However, we can't just jump to our end factored form because we have this a term that is not equal to 1 in this case, right? So instead, what we need to do is break this middle term into the 2 numbers that add to negative 7. So what we're going to do is we say that 2x squared minus 7x minus 15 is the same as 2x squared minus 10x plus 3x minus 15. So the negative 10 and the positive 3 came from our two factors that multiplied to negative 30 and added to negative 7, right? So because negative 10x plus 3x is the same as negative 7x, we know that this step is equal to this step. And now that I have 4 terms, I factor by grouping. So I look at my first 2 terms and I figure out that, hey, they've got a 2x in common, and I'm left with an x minus 5 inside my brackets. And that means that I'm going to probably want an x minus 5 in my other brackets too. So I could even jump ahead and write my x minus 5 if I was feeling particularly confident with my numbers. So, and then I'm looking at these 2 terms, I'm thinking, oh, what can I factor out of here? I can factor a 3, and 3 times x would be 3x. 3 times negative 5 would be negative 15, so I know that this step is equal to this step. And then after that, I'm going to factor out my x minus 5. So I have x minus 5, and I'm left with a 2x plus 3. So this is my final factored form of my complex trinomial. Let's have a look at an example that's a little bit more complicated. So let's look at an example here of 8a squared plus 2ab minus 15b squared. So similarly to that example with the simple trinomial, when I have an a squared term and a b squared term, that means that my final answer has to have both a's and b's in it. But this is a little bit easier actually to see when we are factoring by decomposition method. So first I go about factoring this using the product sum method, same as before. So I need a product of 8 times negative 15, which is equal to negative 120. And I need a sum of positive 2. So I can go through all of my different factors, and I'll find that a combination of negative 10 and positive 12 will add to positive 2 and multiply to negative 120. And then I decompose my center term by using these 2 numbers. So I've got 8a squared, and then 2ab is equal to minus 10ab plus 12ab minus 15b squared. And then I just need to factor by grouping. So I'm going to factor by grouping the first 2 terms and group together the second 2 terms. And I can pull out, well, they both have an a in common, and they both have a 2 in common. So I can pull out a 2a. And then I'll be left with 4a in my brackets minus 5b in my brackets. So once again, I know that I'm going to have 4a minus 5b if I did this right in my second bracket. So let's look at what these 2 terms have in common. So I have 12ab and minus 15b squared. So they both have a b in common, and it looks like they both have a 3 in common. So I can factor out 3b. And 3b times 4a would be 12ab, so that's good. And 3b times negative 5b is negative 15b squared, so that's good. And once I have my grouping factored out this way, I know that my final step is to common factor out that binomial. So I have a 4a minus 5b, and I'm left with 2a plus 3b. And that is another example of a complex trinomial that has been completely factored. So, what have we gone through so far? we've talked about common factoring check, simple trinomials check, difference of squares check, and we just did grouping and factoring by decomposition. Last but not least, let's talk about perfect trinomial squares. So this is what happens when we have a trinomial that is of the form a squared plus 2ab plus b squared. So what does that mean? That means that our first term is a square, our second term is a square, and the middle term is 2 times the square root of the first times the square root of the second, right? So we're going to have, essentially, this is going to be factored into something that looks like a plus b squared. And this is what is called a perfect trinomial square. So let's look at some examples of that. All right. So, perfect squares. A squared plus 2ab plus b squared. So let's look at the example of p squared minus 10p plus 25. Focus that up. There we go. So p squared minus 10p plus 25. So when I look at the first term, I see that it is a square. It's the square of p, right? So that means that I have an a term that is equal to p. When I look at my last term, I see that it is also a square. So that means I have a b term of 5, right? 5 times 5 is 25. P times p is p squared. And then when I look at my middle term, well, minus 10p, I guess this one could also be a negative 5, right? Negative 5 times negative 5 is 25. Minus 10p, that is equal to 2 times a, right? 2 times p times b, which is negative 5, right? So that means I have a middle term that is equal to my 2ab, and I have a first term that is equal to my a squared and a third term that's equal to my b squared. That means that this is a trinomial that satisfies the requirements of a perfect square. Now, if you can recognize a perfect square, that means that you don't need to do product sum method for this. You can just jump straight to writing it out as the square root of the first. In this case, it's going to be a minus because we have a minus in the middle. Minus 5 squared. Recognizing perfect squares does take some practice. However, the more you get used to recognizing them, it does make factoring go a lot faster. So let's look at another example. Let's say we have 4a squared plus 28ab plus 49b squared. First, we want to check to see if we can common factor anything. I know that I've got 4 in common with those first two numbers, but 4 is not in common with the last number. I've got a's in common with the first two numbers, but a is not in the last number, so I can't common factor. However, I can recognize that my first term is a square, right? The square root of 4a squared is 2a. The square, and my last term over here is also a square. My square root of 49b squared is 7b. And then this middle term, 28ab, well, that's equal to 2 times 2a times 7b, right? 2 times 2 is 4. 4 times 7 is 28. A times b is ab. So that means that this satisfies all the requirements of a perfect square. And I can just jump to the factored form. So the factored form of this is just 2a plus 7b squared. And then it's done. All right, so your homework for tonight is a worksheet on factoring. So do make sure that if any of these forms of factoring are an issue for you, go back to the part of the video where we were talking about that specific kind of factoring, right? In general, if there was an order to how do we know if we're going, like how do we know which kind of factoring to use, my advice for you is to always start with common factoring, right? This should always be your go-to. This is your number one. This is your number one kind of factoring, right? Once you're done looking at common factoring, check to see if it is a binomial or a trinomial. If it's a binomial, then check to see if it is a difference of squares, right? Is it a difference of squares? Right? If it is, then you can factor it as x plus y times x minus y. If it's a trinomial, then check to see if it's a simple trinomial or a complex one, right? If it's a simple trinomial, if x squared plus bx plus c, if it's a simple trinomial, that means a equals 1. You can do perfect product sum method, right? And if it's a complex trinomial, if a is not equal to 1, you can use decomposition. And then if it is not a binomial or a trinomial, if it has more than 4 terms, or at least 4 terms, 4 or more terms, then you can factor by grouping. Or at least check to see if you can factor by grouping. It is possible that maybe you are given a polynomial that can't be factored at all. But at least go through this process of first checking to see if it's common factoring, then checking to see if it's a binomial or a trinomial, or maybe something else. All right. Good luck, everyone.